solving a problem as one of the examples where you can, in fact, completely and exactly generate the solution, exactly, of course, within the assumptions that we make. And that was the case of an isotropic plate with a point load on one end and a distributed load on the other. And we said this one is a reasonably common situation relating to the stiffener termination problem, where stiffeners in plates adjacent to this one at the top here would be terminating here. So the load from each stiffener would have to find its way into the plate that is shown here. So it would end up being some kind of a very localized load. And that localized load would mean that the stresses would be relatively high in the region next to that point of action of that force. And it would be necessary to come up with the reinforcements. So we're trying to see if through this solution we can at least get a feel for the size of these reinforcements. And after deriving the governing partial differential equation, we showed that the general expression is in terms of a Fourier cosine series here, and then using the equilibrium equations we can determine the other stresses. And at this point we had satisfied all the boundary conditions. If you look at the sigma y on this edge and on this edge, you will see it's 0. And if you check on tau xy on all edges, you will see it's 0. But we had not satisfied the conditions related to sigma x, which would allow us to determine finally k0 and an. And k0, again from Fourier cosine series theory or from simple integration, is the average stress. Basically, if I integrate with respect to y from one end to the other at any x location, this integral of the cosine 2n pi y over b from y equals 0 to y equals b from one end to the other would be always 0. So the second term means that the average stress has no contribution from this second term, and therefore what's left is this constant. So the constant has to equal my average stress at any x location, the average sigma x stress. And I know my average sigma x stress as being equal to the total force divided by BH, where B is the width of the plate and H is the thickness of the plate. So that fixes K0, and with that known, we can now go through the Fourier series property of each term in the series being orthogonal to any other. And if I multiply my sigma x with this cosine 2q pi y over b, where q is an integer, then this integral will only give me non-zero contributions when n equals q. Of course, to maintain equality with the left-hand side, I still have to multiply with cosine 2q pi y over b. So I multiply by this quantity both sides and integrate from 0 to b almost arbitrarily. But we know that when you integrate, then all the integrals will be 0 except the ones that have n equals q. When you do that, you will then find that this term will only give you the area under this little square, basically, because it's sigma x at x equals 0. So you will get this, which would then, substituted in solving for an, which is here, you will get all the an terms. Basically, the summation disappears because the right-hand side will only contribute when q equals n. So for only one n value at a time do you get a contribution. That then we can put it back into our stresses and have the complete solution. Our first check or our first evaluation before we proceed has to do with to what extent we can reproduce at the edge, at the top edge here, this step stress. So it's 0, and then it goes to a constant value and then comes back down to 0. And this helps us to pick the number of terms, because obviously as you increase the number of terms, you will get up closer and closer to the exact solution. But as long as we get close enough to this step distribution here, or step function, then we don't need to keep adding more terms, because obviously computationally it takes time. So the different cases here start from 10, I guess, and go up to 160. And you will see that, yeah, we're getting closer and closer as the number of terms increase, but even at 160, we are not perfectly close. But arbitrarily, I will say that 80 terms is sufficient, and now it remains to check whether with 80 terms, in this case, we get good enough answers. So let's compare with finite element model, which is the easiest in these cases. As a parenthesis, the laminate we're using has 4 plies of plus or minus 45. A designation with parentheses in this course would mean a fabric ply. So this is a fabric ply. It's a single ply, not 2 plies, 1 plus and 1 minus. And by the same token, if I ever write this in parentheses, that is a single ply in the 090 degrees. So basically, plus or minus 45 means that in a single ply, the fibers, half of the fibers are going in the plus 45 and half of the fibers are going in the minus 45. That's this guy here. And this one, hang on, let's go down this way, is the same thing rotated by 90 degrees, obviously. So it's like this. So the example has only 45s, basically 4 layers of this thing on top of each other. The reason for doing that in this case is because D16 is D26, so I know is D26 is 0, so I know that my assumption that went into the problem solution is definitely valid in this case. I'm plotting my axial stress, sigma x. Remember, x is running in this direction, and I'm starting from the top. X equals 0 is here. And I'm plotting it as a function of distance, x over a. So x over a equals 0 is where the force is acting, and x over a equals 1 would be at the other end. So this is the other end of the plate, this is 0. And it goes to some value, which is the axial stress divided by the far field stress. So basically, the far field stress here is the force divided by the cross-sectional area. And at the other end, where the force is applied, then we get almost 9 times that value. So if you want to think of it as a stress concentration factor, feel free. The point is that the maximum stress is at the point of action of this concentrated force. And in this case, is about 9 times, 8.5 times the constant average stress far field away from the point of action. If you look at the results, the calculated with our methods with infinite series is extremely close or very close to the finite element with small differences in this region here. And one thing we already observe is that we get to that far field value of 1 at about half the distance away from the point of action. So at about 0.4 or so, in fact at 0.3, when we are already very close to the far field value. So whatever an effect this point stress acting, this point load has, it's really significant only within the first 30% of the distance from one edge to the other. So this is an indication of the kind of reinforcement you would need. There's no point in reinforcing from here on, which would correspond to some point in the middle of the plate and moving towards the bottom end, because the stress there is already reached the far field stress. So that's the one that you would design for anyway, and there's no point in reinforcing there. But there is definitely a reason to reinforce from 0 to about 0.3 or so, at least for this specific laminate and for this stress. Remember, there's a whole bunch of stresses. There's a sigma y and tau xy stress that we also have to double check and see what they look like. So this one is the shear stress, hopefully. Yeah, this is the shear stress, again divided by the far field stress. And it's plotted as a function of y over b. So we are going from left to right. And it's done at x over a equals 0.0075. So we are not exactly at the top edge, but very close to it. Now, why are we not exactly at x equals 0? Yeah, exactly. There's no point. We know there it's 0. So plus the exact value there is where the Gaussian integration points were in the finite element model, where we know the solution from the finite elements is exact within the finite element concept. So it would be the most accurate location closest to 0 in this case that we can then use. And you can see that the two solutions are on top of each other. Now this is telling us that whatever these shear stresses do, it happens only 0.3 away from the one end and up to 0.7 or 0.6 or so, between 0.35 and 0.6, whatever. It's only in this region that these shear stresses are significant. So as far as the y reinforcement or the reinforcement in the transfer in the along a y coordinate, we would only need to reinforce the center of the plate, which you would expect because the point load is at the center. Then you would need to reinforce the center. The question is, though, how far on either side of the center should that reinforcement go? As far as the tau xy stress is concerned, you don't need to go any further to the left of this point 0.3 here or to the right of this point 0.7 because the stress there is 0. So now we're starting to not only get a good feeling the solution is good because it matches the finite elements, but also to get a good feeling for what kind of reinforcement we will need. And then we take a case of the sigma y stress. So that's sigma y. Remember, my x is going up, my y is transverse. So sigma y is the normal stress in this direction. And again, this is plotted as a function of y over b. At the same location, x over a equals 0.0075. There's a bit of a difference between the finite element prediction and the calculated, but it's quite small. And you can easily expect if you increase the number of terms, you would get better accuracy. But you can also argue that perhaps the finite element mesh, even though we checked for convergence, perhaps that could use a bit of an improvement on the type of element used and the mesh size also. Again, the sigma y stress is very close to 0 if y over b is less than 0.2 or so, or greater than 0.8. So there's again a region in the center of the plate which would require reinforcement to cover sigma y. Now you can see also at the same time that sigma y and tau xy do not necessarily correspond to the same region in the center in which they are appreciable. One was from tau xy was from 0.3 to about 0.6 or so, 6 or 0.7, while the sigma y is over a slightly larger region. So on the one hand, we have a warm enough feeling at this point that our solution is good because it's close, if not very close, to finite element results. And on the other, we think that by looking at what regions along x or y the stresses are appreciable, we can determine the regions that would need to be reinforced. So now we open up our design space, let's say, and we try different laminates. And to run this now with the solution we have would take seconds instead of hours by the time you set up and for the finite element model. And so I'm doing only 3 different laminates just to see the different trends. This doesn't mean you would only use those, and you would need either a more rigorous way of picking your laminates or definitely some other perspective that says, okay, if for some reason we need to use this type of laminate, make sure you include it in the ones you compare. What I've done here is I've included the plus or minus 45.4, which is the one we have been checking so far to compare with finite elements, which is a very soft laminate because the fibers are in the plus or minus 45 direction, then in plane in the 0 and the 90 direction has relatively low stiffness. Then I have this plus or minus 45, 0, 90 symmetric, again 4 layers, and that one is by definition quasi-isotropic. The 0, 90 is the one that we mentioned here. So we have 2 layers of this and then repeating symmetrically. So that's the quasi-isotropic with the same stiffness in every direction. And finally, we have a 0.94, so it's the same one as the plus or minus 45.4, but rotated by 90 degrees. So that one now gives us the highest stiffness that we can get using fabric material in the x and y direction. So this would hopefully cover a wide range of stiffnesses. If you're using fabric material, if you're using unidirectional tape, then you have a larger range of stiffnesses than you can check. We're plotting axial stress. as a function of distance from the point of action of the force. We already saw the dependence from the plus or minus 45.4, and they all have similar dependence, but the distance over which they die out to reach the far field stress, or the distance over which they eventually go to 1, because this is normalized on the y-axis, is different. In fact, the 0.94 takes much longer, and it would therefore require a longer reinforcement than both of the other two. The other two seem to take about the same distance before they reach the value of 1 or reach the far field stress. So they would need a significantly lower length of the reinforcement. If I now look at my transverse stress, that's the sigma y stress, as a function of my y distance, again I see significant differences. Now the plus or minus 45.4, it has the highest peak, but it's confined in the narrowest region around the center, while the other two have lower peaks and they again go further out, so they would need larger reinforcement in the y direction. Notice the one that is the narrowest is the plus or minus 45.4, which basically goes to 0 very quickly. But in the previous plot, the one, well, that goes from my point. I wanted to say something like this one is not the best one here, but okay. Plus or minus 45.4 is the shortest distance here. 0.94 is the longest. And if I go the right direction, plus or minus 45.4 is the shortest here. 0.94, which is this one, is about the longest. It's about the same as the other one. So obviously, as you are trying to evaluate the size, you would not just do one location, location x over a here is 0.005. You would have to check out 2 or 3 locations, starting from the top here of the laminate with a low applied load, to see indeed that there is no location where the stress is wider. Typically you would expect from intuition, and that's what you would find in results, that only really close to the load application will you have the biggest values for the needed reinforcement. So if you stay close to the x over a equals 0, that would give you the biggest sizes you would need. So unless you really want to optimize the reinforcement and make it have the widest size at x over a equals 0 at the top, and then as you move away from that edge, it becomes narrower and narrower to follow the stresses reducing, you can do that. It's just much more costly, but it's also the most efficient if you are trying to reduce weight. So we saw the sigma x, we saw the sigma y, and then there is the tau xy, the shear stress, where pretty much they all are confined in approximately the same region, which is not necessarily the same region as the sigma y. So you would have to find the worst one among the different stresses for each direction of the reinforcement, the x direction or the y direction of the reinforcement. If I'm taking all this now as a reasonable, good indication of the first sizes that I would need for reinforcement, I can summarize my conclusions that axial stresses in the 0.94 panels decay more slowly, so they would require longer doublers, while the other two faster. We just saw that. But the transverse and shear stresses in these plus or minus 45.4 and the plus or minus 45.090, the quasi-isotropic panels, are more critical in terms of the peak values. Preliminary doubler reinforcements, then the length along the x would be about 0.5 times a, that's 50% of the length of the panel would have to be reinforced for the 0.94 laminate, but only 30% of the length would have to be reinforced for the other two laminates. And the width portion would be only 0.3 b. That's about 30% of the width at the center would have a reinforcement. As I mentioned when we started talking about this problem, the fact that I moved the stiffener, I terminated the stiffener, not only means that I get an axial load from the stiffener transmitted to the plate, I also get a bending moment because of the eccentricity between the neutral axis of the stiffener and the neutral axis of the skin. That bending moment is not included in this analysis, so one would have to include that or read the master's thesis that a student of mine did a couple of years ago. The other important aspect, which actually is one of the major drivers, and we will see towards the end of this quarter, is that when you transfer a load from one component to another, that happens by developing shear stresses. Typically, it's like a shear lag problem. And then in order to balance the moments locally, you will need to develop normal stresses. So at the interface between the stiffener and the skin, making sure that the load which was in the stiffener eventually finds its way in the skin means that you will need to develop out-of-plane stresses. And as we said many times in previous lectures, the resin, which is the only connection between the stiffener flange and the skin, being the weakest spot, will most likely fail or has a tendency to fail. So the final aspects of this design would actually require determination of these stresses and the tendency to create a delamination or failure of the matrix in between the stiffener and the skin. But the purpose of this exercise was more to see a solution, complete solution of the governing equations more than anything else, which we did here. But as I'm emphasizing, you need to address also the bending moment and the interlaminar stress issue to complete that design problem. Another case that we will try to solve exactly involves a plate with a point force, transverse or vertical point force, which can be anywhere acting on this plate. We assume again a symmetric layup, so the B matrix is 0. We assume that D16 and D26 is 0. And why do we bother? Is because, first of all, walking loads, step loads, especially if you have high heels, which is concentrated, quite concentrating the load, are essentially a floor with a point load. More importantly, impact. Impact is, of course, a dynamic problem. We'll talk about that in the next quarter much more. But as a first cut, especially for a series of impact problems called low-speed impact situations, you can start the solution by trying to solve this problem of a point force acting on a anisotropic plate. And we are assuming simply supported conditions. And we need to get our governing equation. Now, we saw the governing equation before. Where am I? If you look at the bottom here, this part is what is derived here, and this part is what we will be using in here. But to see more exactly what's going on, from the equilibrium equations shown here in terms of shear forces and bending moments, we have this equation. QZ is, minus QZ is the out-of-plane load. If I take my QX and QY definitions, or from the equilibrium equations, which are in terms of the moments, I can substitute in this to arrive to this equation here. Now, in the slides posted, this says 0. It's obviously a mistake. It should say minus QZ. It's the right-hand side of this equation here. Now, each of the moments can now be replaced through our ABD matrix relationship. And because we said the B matrix is 0, then it's just directly involving the D11, D12, D16 terms and so on. And because I said D16 and D26 is 0, I can replace these moments with these products, D11 times kappa x plus D12 times kappa x, kappa y, and so on. When we do this, we arrive at exactly the same left-hand side that I just showed you from before. And the right-hand side is still my out-of-plane load. Now, our out-of-plane load in this case is a point force. And I can write that as a distributed load, the word distributed in quotes, by using Dirac delta functions. If I take my magnitude, the force F, delta x minus x0 means that this quantity is 0 everywhere except when x equals x0, in which case it's equal to 1. And similarly, delta y minus y0 is 0 everywhere except y equals y0, in which case it's equal to 1. So that's a convenient way of writing a load, a point load, in terms of a distributed type of function, which becomes very useful in the next slide. We said it's a simply supported plate, so we will assume now for a solution to this governing equation, a solution that satisfies simply supported boundary conditions. W is the out-of-plane deflection, and at x equals 0 or a, and y equals 0 or b, because of the signs being present, W is 0. So that satisfies the boundary condition. And this one, compared to the previous one, which was a single Fourier cosine series in y, now it's a double Fourier series because I have both the x terms and the y terms in terms of signs in this case. That allows me to go back to my governing equation at the bottom left here, and substitute for W all these derivatives of W. But you can obviously see that these then would give me double summations of sine terms. And on the right-hand side here, I have this peculiarly looking expression, which is just a point force at one location. So the only way to proceed, if I want to insist on this Fourier series business, is to actually replace this with its corresponding Fourier expansion. Remember, the advantage of the Fourier series is that if you have any function that's reasonably well behaved in terms of its continuous or its piecewise continuous and its first derivative somehow can be defined everywhere and so on, then that function can be represented by a Fourier series. So we will do the same thing here and replace this by a Fourier series. The Fourier series will have this form, and the BMN are unknown coefficients. And we use on purpose the signs here because we have signs in the W expression, so that when we substitute in the governing equation, we'll be able to match terms of the same coefficients of the same term, sine times sine. To determine the BMN, we go back to Fourier series theory, which says take your infinite series, which is shown here, multiply each term by the orthogonal function. So wherever I have a sine m pi x over a, I'll multiply by sine, where is it? Sine p pi x over a, where p now is an integer. And similarly for the y dependence, I will have my original sine n pi y over b, but I also add my sine q pi y over b. I multiply that and I integrate over the entire plate. If I did it on the right-hand side, I have to do it on the left-hand side also. Remember, all I'm doing is I'm operating on this expression here. I take this expression in order to find BMN, multiply both sides by sine times sine of different integers, p and q, and integrate over the entire plate. Now, from Dirac delta functions in your basic physics, I hope you remember that the integral of a function that involves the Dirac delta function means you evaluate the function at that location. So basically at x equals x0 and y equals y0, I will just, this double integral becomes f because that's my constant, and then these signs will be evaluated exactly at that same location. Now notice I have p and q there, and now this became m and n. It became m and n because my right-hand side will only have a non-zero contribution when m equals p and n equals q. So there's no need to stick with p and q because the right-hand side would be 0. And I will only, and I'm trying to calculate BMN. So I can replace directly the p and q on the left-hand side with what I know from the integration on the right-hand side will be my only non-zero terms. To make a long story short, my BMN times AB over 4 has to equal this left-hand side, so I can calculate my BMN. And knowing my BMN, I can go back to my series expression here, substitute W in my governing equation on the left-hand side, substitute the BMN sine times sine on the right-hand side, and equate now the coefficients of the different terms of, that have sine m pi x over a and sine n pi y over b. When I do that, I will find now that my a and n terms, which is what I was looking for in the first place for the W expression, are given by this mess, as a result of which my W now, just by taking this and putting it in, is given at the bottom of this page, and that's valid for any xy location and for any x0, y0 location where the point force is acting. Of course, the special case is the force acting in the middle, which gives us the largest deflection. In that case, by substituting x0 is a over 2 and y0 is b over 2, you can show that this is the center deflection. Remember, that's for a simply supported plate for which D16 and D26 is 0, and the layup is symmetric, so the B matrix is 0. So, okay, big deal. You got W. You were talking earlier about impact. So what do you do with this? Somehow, I have to relate my impact energy, this dropped object, to a certain force. Once I know that force, the maximum force during impact, I can do the solution I just did. That gives me the displacements. And that's not even half the story. I have to translate these displacements into usable strains through the structure, which is mostly what you are doing in your homework 1 right now. So I make the W's into strains, and once I have strains, I can then either use them in a strain-based criterion or translate them further into stresses if I want through stress-strain equations, and use a stress-based criterion, and that will give me an indication of which ply fails. And again, the next step would be, okay, I failed at some location, what happens next? And that's where we'll talk about in the second quarter, the next quarter when we talk about impact. But this kind of starts giving you the logic, and it can be quite useful as a starting point for the real impact problem later on. There's one more example. And before doing that, because we will use energy methods, I will repeat some of the basics of energy methods. Some of you, if not most of you, have seen them in the second year, because I use pretty much the same slides on this part. So consider it a reminder. The governing partial differential equation is almost impossible to be solved in any kind of a general case. The cases we saw here were interesting because they actually relate to some useful problems and you can solve them exactly, and there are very few cases like this. So you need other methods that allow you to solve these equations approximately and reasonably accurately. And that's where you say I can use my finite element model, and you are very welcome, if not good for you doing it. But if you're trying to get a feel of what the solution should be to compare, let's say, your finite element results, then you would need some solution like this. Or if you're trying to do an optimization problem where you need to run a relatively fast solution many times, you can't afford to keep running your finite element model every time. So, plus I guess the main thing is you solve with your finite elements and you go show it to your supervisor and they tell you it's wrong and they don't even tell you why. And then the only way is to check this way, because that's what happened to me when I started in industry back in 1984. I had this wonderful solution with my finite element model. It was the first years that people were using Patran at the time. And my supervisor, a guy from England, looked at it and used a word that starts with the word bull and then 4 letters afterwards. And I was quite good as a student, as a master's student and undergraduate student. I had gone to a good university, so I was a bit upset and disappointed how he could just by looking say that the results were wrong. And he said, go do something and don't come back until you fix it. It took me a week and I had to go through a solution like this, which was approximate, but at least showed me, first, my boundary conditions on my finite element model were wrong. And second, the way I was applying the loads, I was presupposing the displacement pattern, which was not necessarily correct. Now, this guy was 20 years older than I am, and he could just tell by looking at it. So you have an option. Either you develop the intuition, and then you just do finite elements and use your intuition, or you develop enough understanding of the basic methods that you can use to check solutions like your finite elements. One of the methods is energy methods. We have 2 types of energy. In fact, we have a whole bunch of them, but the 2 of interest are the potential energy and the complementary energy. And basically, you can minimize either of them. Potential energy basically means you write your energy in terms of displacements. Complementary energy, you write it in terms of stresses or forces. And the theorems say, this is one way of stating them, say that in the first case, if you want to satisfy all the governing equations, you have to pick. Some of them you'll satisfy them exactly, and some of them you'll satisfy approximately. If you choose to satisfy approximately, your strain compatibility, and strain compatibility means this equation here. For a two-dimensional problem, remember we said last time that if you eliminate the displacements, you can come up with a relationship that combines only the strains. So that is the equivalent of the strain displacement equations. So you can satisfy that exactly, which means you are making a displacement-based solution, which most finite element models actually do. And you can satisfy your geometric boundary conditions. That means any boundary conditions on displacements. You don't do anything about boundary conditions on the forces. Then you choose to satisfy your equilibrium equations approximately, which means you will minimize the energy. And if you minimize the energy, the result will, on the average or in an approximate way, satisfy your equilibrium equations. So, equilibrium equations, strain displacement equations, stress strain equations. Of those, I pick the strain displacement equations or the strain compatibility to be satisfied exactly. And then I will satisfy my equilibrium equations approximately if I minimize the energy. Now you might say, what happens to the stress strain equations? They are still there. They just are a property of the material. They allow you relating stresses and strains. So as long as you use displacements to go to strains and then eventually to stresses, you will use them and they will be satisfied. So don't worry as much about the stress strain equations. The flip side of this is, okay, instead of satisfying the compatibility, strain compatibility, you choose to satisfy equilibrium. So first you satisfy stress equilibrium equations and all your boundary conditions for forces or moments, but you don't necessarily satisfy boundary conditions on displacements. It's not necessary. Then if you minimize the energy in terms of stresses, though, you will actually, on the average, satisfy the strain compatibility. Now, all this sounds like philosophy and relatively boring, but it's the basis of all good approximate methods we have. Finite elements are based on this. The methods we'll be talking here are based on this. And recognizing what you assume and what you satisfy is important because sometimes you will get incompatible results and you don't know why. So if I summarize, the exact situation would say I have equilibrium equations, strain compatibility condition, which is the strain displacement equations with the displacements eliminated, the force boundary conditions, displacement boundary conditions. If I satisfy all these exactly, my energy is minimized. I don't even need to minimize it. It's minimized. The result I found minimizes the energy, and the solution is exact. Now I choose to invoke energy minimization here to eliminate one of these columns. So if I satisfy equilibrium equations approximately, that means I'm doing a displacement-based solution and I satisfy exactly my strain compatibility, I definitely need to impose the boundary conditions on displacements to be satisfied exactly. Minimizing the energy will do two things. Will satisfy approximately my equilibrium equations and will satisfy my force boundary conditions on an average sense. That is, point by point, you might not get a force being zero at some location, but if you were to integrate at that location through the thickness, you would find that that integral is zero. The last option, the complementary energy, if you minimize the energy having satisfied your equilibrium, stress equilibrium exactly, you end up having satisfied strain compatibility approximately and the displacement boundary conditions approximately. And that would be, again, an approximate solution. Which of the two you use depends on what is easier, to assume something on the basis of displacements that you think represent the structure, or assume something on the basis of stresses. We'll be doing some stress-based minimizations in just a second and also later on in the course. The book has the whole complete derivation. This is the displacement-based energy for a laminate. You can take it for granted or follow the derivation. The main thing is what in an isotropic material would involve it's always a product of stress times strain that goes into the energy, and that, if you do it in terms of displacements, would be epsilon squared over, no? you would have terms like Young's modulus times epsilon squared. And you know, for example, that epsilon x is du by dx. So you would expect to see a du by dx squared term, there it is, and there should be the equivalent of a stiffness here, which is the A11. Now this is stiffness per units of Newton per meter instead of Newton per meter square, so it's stiffness times length because it's already been integrated once. Remember, energy is a triple integral dx dy dz. So if one of these has already been eliminated, then instead of having E involved in the integrand, I will have the A matrix. So this top line involves the terms that we would consistently know to find in a plate problem in isotropic material in a membrane kind of situation. The bottom, very bottom one, which involves now the curvatures, there is an equivalent to this kind of derivation that usually we know it in terms of m squared over 2ei if it's a beam, and again this is integrated over the length of the beam, or instead I can write my moment as a d times d2w dx squared term. Moments like mx is d11 d2w dx squared with a minus sign and so on. So from isotropic materials we know that the energy would involve terms like this. In anisotropic I would expect to have terms like this, which means I have the second derivatives of w squared, which you can see are there, and then I have a d which in an isotropic material is e h cubed, the thickness of the plate, over 12 times 1 minus nu squared. So if you're doing an isotropic material in bending, there is a term that will always appear, which is the d, the so-called d. The corresponding one now, because this is squared, and there's one over here dividing it, you can see that the corresponding term will be the d11. So if anybody has seen the metal expressions, these are equivalent and analogous, but they are not easy to derive if you don't start from first principles. Membrane energy, so energy stored in extension, in plane shearing or contraction of the plate. Bending energy stored in bending in any direction or twisting. And then the coupling, which is the green mess in the middle, which involves the B matrix. That's the one where you actually combine now in plane displacements U and V with out of plane displacement W. So while the top line only involves the in-plane displacements U and V, and the bottom line here involves the W displacement, in the middle we have them combined. And you can see how that really complicates things and why it's very advantageous from a mathematical algebraic perspective to actually have a B matrix equal 0. That's the general expression if it's in terms of displacements. Having said this, we will now do a problem where we will use the expression of energy in terms of stresses, but instead of actually showing you the expression, we will have it come up in just a little bit. The problem we want to solve is of a plate, a rectangular plate, which consists of two different layups. There's one layup in the middle and one layup on the outside. Dimensions are shown here, 2a, 2b with little letters, and 2a capital and 2 capital 2b for the inner layup. And they can be anything they want. And we will also define normalized coordinates. Xi is x over 2a and phi is y over 2b to simplify some of the calculations. It's simply supported all around here at the edges, outer edges, and we apply a constant force on one end, NA, which is the force divided by 2b. Remember, N is force per unit width. So I apply a constant force F, which divided by my 2b width gives me the applied NA. And we want to calculate the stresses everywhere in this plate. Now, why we want to do that, we'll see in 15 minutes. Continue. We'll actually look at the news again. This goes back to December, but we'll eventually catch up with the news of today, but not today. Airbus And MIT looked to digital manufacturing to reduce aircraft construction costs. That's great. Could composite aerospace structures be assembled much like snap-together building blocks? You know, it's my son's paradise. I mean, Legos. Rather than manufactured as large, expensive one-piece parts. Now, we will revisit what it says here, large, expensive one-piece parts, in a little bit. Hopefully, if I remember. Under a new research agreement, Airbus and MIT will explore the potential of digital manufacturing in aircraft construction. Aircraft manufacturers are increasingly adopting composite materials to reduce aircraft weight. Current composite airframe manufacture involves the fabrication of large single-piece parts, an expensive process. Okay, let's talk as we go. Composite manufacturing is significantly more expensive than metal manufacturing, even today. So you guys are the experts. We've taken 10,000 courses, and I would like you to tell me the reasons why composite manufacturing is more expensive than metal manufacturing. I have 45 people here that are refusing to give me any idea. I'm going to talk to your parents. Yeah. Okay. Okay, but even if I automate, I mean, you have to think, okay, the automation itself, since you mentioned it, the automation does not give you the same efficiency as in a metal because you are not as flexible yet. The automation equipment, robots and fiber placement and so on is not as flexible as what you might do machining a metal structure. But, okay, that's automation. I'd say even if you did have automation, we are not still competitive enough with metals. Tuan?
There I guess more steps involved, like cleaning the surface, applying vacuum bags.
Okay, now we have a whole bunch of more steps in the process, and that's important. Any other? Back again?
We need to apply safety factors for composites with regulations.
Okay, and that's actually indirect, but it's reasonable. The safety factors, or at least the requirements, are more stringent with composites, impact damage and so on. And that typically adds weight. And every time you add weight, usually you add, not proportionately, but you add some cost because you have more material you are putting in and more time you spend to put that material down. Other reasons? I want at least one more. Way back there. Okay, very good. The cost of raw materials, it's at least a factor of 10, even in the cheapest form, it's at least a factor of 10 more expensive than the cheapest metals. In fact, aluminum is about 1 to 3 dollars per pound, so that would be pounds, is about 2 to 6 euros per kilogram. Steel is about half that, but we don't use much steel because it's very dense, and titanium is it's about 10 euros per kilogram. Now composites, the cheaper composites, if we're on a good day, would start at about 20 to 25 euros per kilogram. Now some people will tell you, I have this miracle material which is based on natural fibers and matrix that's just a variation of water. Yes, there are materials, but those are not strong enough. Those have not been demonstrated to last 30 years and so on. So the good materials of today, composites, are expensive. Having said that, that doesn't mean that that's the main reason. In fact, the reasons are more what the front here said. But raw material is usually about 12% of the total cost. So if the raw material is 10 times more, still you are paying more for the final product. The steps in the process and the complexity of having to make a part that's not flat anymore adds a lot to the cost. So composite manufacturing is expensive, and there's one aspect of the manufacturing process, the assembly. If I make something, I need to connect it with something else, and the assembly process is quite expensive. In fact, roughly you can assume it takes about a minute per fastener and to put something together. So if you have thousands of fasteners, there's thousands of minutes worth spent. You might argue, okay, I will do bonding, but if you do bonding, then your structure cannot be easily demonstrated to be damage tolerant. You cannot prove today without destructive testing that any bond line is not the so-called kissing bond. Basically, if I have perfect coverage with adhesive, it does not mean that the adhesive has adhered to the parts that it's going to connect to. And there is no non-destructive method today that's been demonstrated to work in those cases. Therefore, if you choose to go with a bond line in primary structure, you will have to demonstrate that if you lose 50% of it, you can still meet limit load. And usually that's too heavy to do. And you end up having to put fasteners, the so-called chicken fasteners. That's why it's chicken, because we chicken out. We know that the adhesive is strong, but we cannot prove conclusively that every day we will make the same part with the same process. We will not miss something, and we won't end up with one bond line on one part being a kissing bond. So we use these fasteners, which allow us to go from limit to ultimate load, essentially, and those are the chicken fasteners. Assembly, therefore, which will involve some form of fastening most of the time, will add to the cost. And in order to avoid the assembly part, we try to make the parts out of composites as large as possible. If you make a lot of small parts, as in a metal built-up structure, sheet metal structure, then you can connect them with rivets and everything is fine. The process is well understood and reasonably fast. If you try to do that with composites, you have the raw material being expensive. You have the extra steps you have to go through the process, especially if you don't automate, and the cost of assembly. So if you can remove the cost of assembly by making larger parts, now you can start making your part more competitive. So there's a bit of a problem that I have, because this is contradiction, involves the fabrication of large single-piece parts. It's done on purpose. If I am making small parts, I have to assemble them. If I have to assemble them, I am adding cost. So the manufacturers are smarter than the article writer here, in that we want to make as large parts as possible to eliminate fasteners, which also helps on your aerodynamics and so on, and to reduce the cost and make the cost of a composite part competitive now to a metal part. The fuselage of the A350 XYWB, for example, is made up of a number of large composite panels which are then joined together. That's an interesting problem, and let's see how much you guys know about composite manufacturing or manufacturing in general. If I'm trying to make a fuselage which has a circular cross-section, option number one is to make it in a single piece. Let's assume that you have the money to have the mandrel or the mold, that you can cure it in a single piece. Option number two is made in two pieces, which are connected, here and here, let's say. Option number three is to make it in four pieces. Now, any of you following the 787, this is the option they selected. And I'm pretty sure A350 is very close to the same one. So, knowing what these guys did, can you tell me what's the best approach? Now, be careful, of course, if you say one of these two, you have a good reason, because otherwise we call Airbus and Boeing and tell them we found a solution. So, which one is the best and why? A room of 45 experts here.
The question is it production perspective or like a structure perspective? Because as a structure perspective, I think it's
Production perspective. Okay, I agree with you. Production perspective, cost perspective, and okay, you think the gentleman over there.
There's tolerance problem. If the first one doesn't work, then you lose the whole thing.
Okay, that's very good. I would call it risk related. This is a big fuselage, even if it's a barrel, so the length perpendicular to the page is not very big. This is huge. If something goes wrong during all these steps that were mentioned that I have to go through, and I either don't notice or it's too late, then I waste millions of euros in labor hours, parts, materials, and so on. The risk associated with this is very, very large. Not to mention what I skipped, of course, that creating a mandrel of this size and making sure that it gives you the right geometry with the proper heat-up rate during curing, it can be quite challenging. So this is not the way to go. How about this one compared to this one now? Remember, we said the fewer the parts, the better, because the assembly is less. But we already said that if we make them too few, the risk is high. So obviously I have two extremes here, but there's one more reason which is related to one of the words you mentioned. I make one half here and another half there, which presumably are identical. One.
Oh yeah, I assume that maybe
Okay, but that's an afterthought. But it does help to have more lines or to move cracks around if they grow in the wrong way. But before that, suppose I made these and they are nominally identical. They come even from the same mold. Now, when I come to connect them, they will never match. There will be, if I match exactly at the top, usually there's going to be a gap one way or another at the bottom. You might say it's small, it might be only a few millimeters, but few millimeters, if you try to close that gap, is few millimeters worth of a bending moment you put in, and you don't want that on top of your other loads. If you have 4 parts, whatever problems you have, let's say you connect these two, when you connect these and these and these, you can divide the overall tolerance problem in more locations, and therefore at each location you will have less of a gap. So if you do it in a smart way, when you connect these, you don't just connect one and keep on doing that and you collect the complete tolerance here. You do it in such a way that you actually bring it together almost simultaneously, and then you can remove the tolerance problem or reduce it significantly. So these guys, I think, are reasonably conscientious of the cost issues and the implications of assembly, and that's why 4 pieces is probably nearly optimal. Some people might talk about 3, but I wouldn't know. So there's a reason why there are large pieces, and it's not because we can't do it differently. It's because it's actually, given what we have today, the best way of doing it. The digital material concepts being developed at MIT could lead to lighter weight structures and lower construction and assembly costs. Now, this is a great promise. CBA is the Center for BNA, but I don't remember what BNA is. A, I think, is art, because basically what happened is this gentleman, Kenneth Chung, finished his PhD last year, I think, in the Department of Arts and Sciences. And that's where, another parenthesis, architects and civil engineers. Architects are the major problem of civil engineers because they come up with concepts that are structurally completely unsound, and they expect the civil engineers to find a way to solve it. At the same time, some architects will come up with some nifty concepts, and eventually when you implement them, it might give you a really nice result. So I think this is a case where someone coming from not a aerospace or structures related background used a lot of imagination, and being a very innovative person, came up with a concept that actually has a good chance of not being a nightmare for the structural engineers, but the story is still, or the jury is still out. Reversibly assembled cellular composite materials. Okay, so you basically create a 3D lattice of mass production. I'm doing it on purpose. I'm going slowly and I'm not showing what it's all about. See if I can keep you awake on a Friday afternoon. So he produced flat, cross-shaped composite pieces that were clipped into a cubic lattice of octahedron called a cuboct. So if you do a search under cuboct, you'll find some pictures. Here's the interesting part. The parts form a structure that is 10 times stiffer for a given weight. So stiffness to weight is 10 times better than existing lightweight materials. So now I'm starting to get interested and excited, obviously. And they call them digital composites because you can build them up from specific units, and it's like ones and zeros, and you can create anything you want. The MIT technique allows much less material to carry given loads. The cost of construction and assembly would also be lower. That's where it's going to be interesting. I'll show you what the concepts. Oh, important, very important. Unlike conventional materials, the structure will fail locally because you have all these little elements that make up the structure, and you break a few of them, but there's enough of them around to take the load. So that could make a very damage-tolerant design. It also makes it easy to repair because you just remove the portion that's damaged, and because it's all modular and you can add to specific locations very easily, then you can any piece that's broke. Okay, but what exactly does it look like? So this is the building block, which is this gizmo here. It's a flat piece composite. It has a slot in the middle here, and then these shaped lugs, whatever you want to call them, with slots. And they put them together any way you want. And one example shown on the right there. So you can create a construction which will have pretty much any shape, of course still maintaining aerodynamic shapes, and how you will put a skin over it it's not clear, but it's still at the beginning. So I have my doubts and questions, but last time I had doubts about a good idea, I was completely wrong, so I am refraining to publicly complain. I showed this to my son and he said, can we get these Legos to play? Yes. I actually, yeah, measured, scaled it. It's about, you can make it in different sizes, but it's about this. So that would make it 15 by 15 centimeters or something. But you can make it smaller. So you can create all these wonderful things. You know, this is the architect. They come up with all these conceptual things, and now the structures guys have to make sense of them. So it's an interesting proposition, and it's also interesting that Airbus is jumping on this because I think it's too early to make a investment or a commitment in terms of, okay, for the X number of years, future years, we'll work on this because it's very promising. But it goes to show that if you think of weird things, sometimes people will believe you and get excited about it, and that is the good thing about some architects, not all of them. So where am I? I can't see. We're going to solve this problem, and the reason we want to solve this problem, I need to find a way to get the sun out of my eyes, is that there is a class of problems that we can directly relate to this. The first and easiest one is, suppose I have a plate which has a rectangular cutout in the middle. So basically my center laminate in this case is 0, it's nothing. Or I have a plate in which in the middle I have a stiffener which just terminates in the middle on both sides. It doesn't extend to either end. In this case, the local stiffening effect of the stiffener could be represented by another laminate of different D-matrix properties. Or I could have a plate with 2 stiffeners at the edges, so now it's the same as this one, but imagine the inner layup extending all the way to the edges, so the green part. The outer layup will be the 2 stiffeners plus the skin. So this would be my outer layup, and the inner layup will be the center portion shown here. Or I could reverse that and end up with the stiffener portion or the stiffened portion in the middle. Now, you can show, if you just do a few trial and errors, and that's how we started working on this, is that you can come up with significantly higher buckling load in a configuration that has 2 laminates, one in the center and one around it, if you pick the laminates carefully, obviously, with the same weight. So it all of a sudden comes up as an interesting alternative, and it would be nice now to come up with a solution that doesn't require finite elements every time. Yes? Or if each skin portion between frames is 0.5 meter length, and depending on where you put your stringers, you have stringers every 15 centimeters, let's say. So you can replace even a single bay, 15 centimeters by 50 centimeters, by this, and if you just put a strip of material in the middle to represent the middle layup, you are saving on the stringers and you are increasing the buckling load. It's not as easy as I made it sound, but yes, you can make it, and in many cases it will work. But it's not a blind thing, let's just add material here, because you will soon find that your buckling load goes down after a while you keep adding material. So it's not an easy problem to find the optimum. You will assume that the inner and the outer layups are both symmetric, so there's no B matrix, and that means that we have only a membrane portion of the energy and a bending portion of the energy, when I was talking about the energy with the different parts. And in fact, in this case, we are only interested in the membrane. We are applying an in-plane load, and we're calculating stresses. We are not doing the buckling check. For the buckling check, you would need the D matrix also. Instead of the expression I showed earlier, so this is which would require on displacement based, you would need the top equation here, or the top line, which involves the A matrix, and that's the displacement based energy minimization approach. If you do a stress based or force based, then the exact equivalent, instead of involving the A matrix, it involves the little a matrix, which is the inverse of it, and it has this expression here. Notice there is no A16 and A26 because we are assuming that there is no stretching shearing coupling, so the capital A16 and A26 are 0. which means when you invert it, the little A16 and A26 are 0. If I use the energy that's stress-based, I have to satisfy exactly my equilibrium, minimize the energy, and then that will satisfy my strain displacement equations approximately. My equilibrium equations are shown here, and we've seen those before. Instead of stresses, I have the forces per unit width, but it's pretty much the same thing. And I have my boundary conditions for forces, which say that my nx at the two ends of the plate will have to be equal to my applied force divided by the width. My ny at the two vertical edges of the plate has to be 0. And nxy everywhere has to be 0. So if this is my plate, I'm loading in this direction. I have a center laminate here. And this is my x, and this is, don't even remember, it doesn't matter, x and y is going up, let's say, and x is horizontal. Then if I only apply the force in the x direction, this edge has no force applied, which means the ny and the nxy here are 0. And exactly the same thing at the top, ny and nxy 0. Also, at the two vertical edges here, nxy is 0 also. So hopefully that's what that says there. Yes, those are the boundary conditions we have to satisfy. Now, you can take my word or you can substitute and prove it that if you use this nx, ny, and nxy, you satisfy exactly the equilibrium equations and all the boundary conditions. In fact, the way I came up with that is I started with the nxy, substituted in the equilibrium equations, find nx and ny, then substituted in the boundary conditions, and then I fixed all my constants that I didn't know at the time. So these expressions satisfy all the equations that we need to satisfy, but the HMN coefficients are unknown, and those are the ones that we will determine by energy minimization. The energy, as I just said before, the complementary energy is this term, but we also have the work done. The work done is force times displacement, work done by external forces, which means I need to calculate my displacement at x equals 2a, and I know my nx at x equals 2a because that's my applied NA. So there's one extra step here. In the end, I will take the derivative with respect to HMN and set it equal to 0. I hope I have the derivation. Yes. In order to do that, I need my displacement u at one end of the plate. So before, when we did the first example, last lecture, epsilon x is given in terms of the A matrix and the nx and ny by this expression here. So if I take my nx and ny from these expressions and I substitute in here and integrate with respect to x, because epsilon x is du by dx, I can find my u will be integral of epsilon x dx. So that's exactly why we are integrating with respect to x to find the displacement. And if I evaluate it at x equals 2a, I will find this expression here, which is also a function of the HMNs, which are still unknown. If I take the derivative of the energy minus the work term with respect to HMN and set it equal to 0, I arrive at a big matrix equation where the first square matrix here comes directly from the complementary energy. This comes from the work done. Those are all known, and the unknowns are all in this vector of HMN. And that becomes a system of m by n equations by m by n unknowns, where m and n now are the terms in the series that you use. And usually for this problem you need at least, or about 30, at least 20 to get it to work. The reason for that, let's have a generic discussion on number of terms. If I'm trying to solve this problem, if the stiffness of the inner layup is similar to the stiffness of the outer layup, then if you think of what way this deforms, it's going to be as if you had, or close, it will deform in a way that's similar to a single material. It's when the stiffnesses are very different that will make a big difference, because let's say the center portion was extremely stiff, while the outer portion was very soft under some load. In this case, all the displacement will happen around here. So a point, this line before loading would pretty much move. This point will stay in this location because it's attached here, and this is very stiff. So it would actually deform like this, and similarly probably something like this on the other end for this originally straight line. That part is the one that is very difficult to capture with a simple function of using a few terms. If I only use sine of pi x over a, one half wave, it would look like this, and it has very little capability of capturing this weird shape of the displacements over there. So that's why you need quite a few terms. And let's do some, we solved it. We used some kind of matrix inversion or Gaussian elimination to solve the system of equations. How good is it? Again, we will compare with finite elements. The center layup, again, it's all fabric plies, has 545 degrees, 2 090s, and then another 5. The perimeter is thinner. It's the same as the center, but instead of 5 plies on the outside, it has a single ply on the outside. It's plain with fabric, and we're using a square plate, and then we are changing the center part to have different dimensions, 5 by 5 centimeters, 10 by 10, 25 by 25. And again, these numbers are weird because they, in English, units are very round, nice and round numbers. So here's my plate. The center square is here, and I'm plotting the nx, or the stress. If I divide nx by the plate thickness, that would give me the sigma x stress, on a transverse line, transverse to the load applied from the center all the way to the edge. And I get 3 types of curves for the 3 sizes of the squares that we said we are using. So the points are our solution, and the continuous lines are the finite element ones. And you will see one important aspect, which is the stresses are discontinuous. And we started with the displacement assumption of a few pages ago, shown at the bottom here, displacement, I'm sorry, with this nx, ny, and nxy. These functions appear to be continuous, but when you actually evaluate the actual HMN, you capture the discontinuity that the stiffness difference causes. And in fact, our solution is extremely good for this case, and for this one, it's a little less good, but still good enough for engineering purposes, definitely, for the smaller of the squares. So this one is the smaller square, 5 centimeters. This one is the intermediate size, and this one is the biggest. And you can tell the size by just looking at when the jump occurs. The jump is where you have reached this point. So this is at 0.5 normalized distance from the panel center. So if this is 50, you can find exactly where that point is. So this is quite good. And we used it to actually design some parts and save some weight. And that's the end of solutions, stress solutions that we can get accurately, exactly, in fact, by solving the governing equations or minimizing the energy. We will now move to a completely different type of failure, which is buckling, and we will start with buckling of plates. The reason for that, instead of starting with buckling of beams, which we will do later, is because some of the buckling of beams cases can be seen easily as special cases of plates, and it's easier to do it that way. This, unfortunately, is not a very good picture because of the lighting on my screen. Looks great. This is a B-52, or a part of it. This is the wing here, and the forward side is here, and people in second-year structures may have seen this before. If you use your imagination, the fuselage here is buckled. It has all kinds of wrinkles, and maybe you can see them. Yeah, here you can see them better. This region and this region. The skin has buckled, and you can see all these wrinkles or the half waves. This is under its own weight, and mainly because this wing is at the top there. And it's done on purpose. That's a case where, to save weight, they allowed the skin to buckle when it sits on the ground. If it's now taking off, and it's funny to see them, when they take off, the wing, as it develops lift, as it speeds up on the runway, it takes forever to speed up, obviously, because it's a monster. As it speeds up, the wing moves up, and as the wing moves up, then you see all of a sudden these disappear. So during level flight, there is no buckling. And here you can see, hopefully, the wrinkles again. That's what the B-52 looks, or profile. You know, you will never win a contest of good-looking airplane. So buckling, it happens very often. It's a very common failure mode. In fact, most aircraft structures are designed for buckling, or the percentage of a structure designed by buckling or stability-related requirements is much larger than anything that's failure-related, except potentially for damage tolerance, which is the second most common failure mode that designs structure. And if you are careful about it, you can actually use it to your advantage and save weight when you do post-buckling, and we'll talk about post-buckling in either the next lecture or the lecture after. We will start with a problem that is a rectangular plate, simply supported all around, so the displacement out of plane is 0, under biaxial loading. And this plate has symmetric layup, so the B matrix is 0, and the D16 and D26 are again 0. And we are following basically the approach. It's in the book in detail, but it's mostly taken after the approach by Jim Whitney, who wrote a book on structural analysis of laminated anisotropic plates. Basically, between him and a couple of other guys, everything that people do in composites is a repetition. These guys discovered everything, and we are just rediscovering the wheel in different small variations. We are doing this problem because then if you can solve the biaxial problem, then the uniaxial problem is just a special case of this. And because it has some interesting characteristics. Of course, if my loading is tensile in both directions, at least for a metal, you cannot buckle it. If you apply tension in both directions, then it just extends in both directions. If one of the directions has compression, then you can get it to buckle. Now, in composites, for some layups, you can actually get them to buckle even if you have biaxial tension, but that's quite rare, and it's not done very commonly. Usually, either both of them are compression, or one is tension, the other compression, and that way you can actually get a buckling solution out of it. Now, the governing equation is this one, which is the green equation we saw before. Let me show it again. So if you look at the bottom here, we have exactly the governing equation in which the distributed loads Px, Py, and Pz are 0, Px, Py, and Pz are 0. And for our problem, we do have nx applied, we do have ny, but our nxy is 0. So if I take this equation and remove these terms, I will end up with this governing equation for W. My boundary conditions, remember, now is simply supported, and that means my W is 0 all around the edges. But also, in the strict definition of simply supported design, where we allow the edges to rotate freely, there are no bending moments there. So the mx is also 0 and the my is 0. So in fact, these are the full set of boundary conditions. And why do I have 4 of them? Because it's a fourth order differential equation. As you might expect, when in doubt, you assume an infinite series with sines and cosines. And because it's a simply supported, if you assume this, then you satisfy all the boundary conditions, both on W and on the moments, because the moments, mx, my, and so on, are just second derivatives of W, either with respect to x or with respect to y. So if W is 0 at the edges, the second derivatives will reproduce the sine terms, and therefore they will also be 0 at the edges. So automatically, with this infinite series for W satisfies our boundary conditions. So I substitute this in my governing equation here, and I factor out the sine m pi x and sine n pi y over b. So if I factor that out and I cancel it from both sides, I will get this mess on the left-hand side equal to this mess on the right-hand side. Basically, that involves the AMN on both sides, and that's not very encouraging because AMN would cancel. And it involves the AR, the aspect ratio. A over B is the length along which load is applied, B is the width, and we call it AR aspect ratio. Now, one solution says AMN equals 0, and that means my W is 0, so I only have in-plane deformation, stretching, and so on. That's fine, but if we're trying to do buckling, that's not the one we want. And the other is AMN is different than 0. So if AMN is different than 0, I have to find a way to satisfy this equation. And before I do that, for convenience, I introduce this notation. NX, if it comes out positive, it means I have tension. Since I want the compressive load to be expressed as a pure number, I call NX minus N0, completely arbitrarily. That means if my answer is in terms of N0, and N0 comes out positive, then I have compression. And I then introduce this NY is minus K N0. Basically, I'm saying that NY is K times NX. So for one value of K, I can find an answer. If I change that value of K, then the answer will change. So if I take this equation here, and there is no sun over there, I can solve for NX, which I can write in terms of N0, and I will find this expression. This expression says my buckling will occur when N0 is equal to this quantity, which is a function of that K. So the amount of NY load obviously affects my buckling load, and the more my NY increases, this K would increase, so the buckling load would go down, for example, for a case of biaxial compression. Notice where the aspect ratio appears in all over the locations, and that's significant because as I change my aspect ratio, will change the buckling load. We'll see that in a little bit. And notice the M and N. Now those are important. Let me briefly mention them now, and we'll talk about them some more later on also. This is my M and this is my N. Sine M pi x over A basically means a function that between 0 and A just simply does one half wave. So if M equals 1. If M equals 2, then between 0 and A I will have two half waves, and so on. So the M and N is the number of half waves in the different directions, in the x direction and the y direction. So if I have a plate can you see, or is it too shiny because of the sun? No, you can't see. We'll do it here. If I have a plate and I look at it by making a cut here, let's say it's under this kind of loading. If it looks like this, this is the shape at this location here. I have one half wave, M equals 1, let's say in the x direction. Now if I were to make a cut and look at it this way, if I saw something that involves two half waves, then I would have N equals 2. And essentially my shape, if I could draw it, would look like this. Looking from the top now, I have one half wave in this direction and two half waves. How do I draw this? I don't know how to draw it. I have two half waves. Yeah, I know. It would look like this. So I have two half waves in this direction, and at any location, if I look at it, wherever I am, I would find one half wave. Now, if these are two, one is coming towards us and one is going away. So the message, M is the number of half waves in the x direction, N is the number of half waves in the y direction. I hate this. Next time I should do something about that. Let's take the case. This is ridiculous. I can't see. Biaxial compression and y equals, okay. Uniaxial compression, that's what that says. Yeah, supposedly. Makes noise but doesn't do anything. Miracle. All right. So this is the case that involves both the uniaxial compression, the compression in one direction and tension or compression in the other, expressed by positive or negative values of K. If I only have single compression, then Ny is 0, which means the K that's shown there would be 0. And therefore, this is my buckling load for uniaxial compression. And if I look at this one now, this buckling load is a function of M and N. Same way this buckling load is a function of M and N. Now, for the case of the biaxial loading, you have to find which combination of M and N values minimize this, and that is the lowest buckling load, or the buckling load in which a perfect flat plate would buckle into. In sense, if you imagine you start from 0 load and you are increasing, then it will buckle when the lowest load starting from 0 is reached. So any expression that you have describing a buckling load, if it's a function of any other parameter, you have to minimize with respect to that other parameter. So in general, you would have to find here the M and N that minimize this, and for non-zero values of K, it's not at all obvious which value minimizes that, because it's a function of the D matrix and a function of the aspect ratio. In the case of uniaxial compression, it's slightly easier. Once K disappears, if you look at this, N appears only at the numerator, which means if I'm trying to minimize this, the smallest value of N, because all the terms involved are positive at the numerator, the smallest value of N, which is N equals 1, will give me the buckling load. So if I have uniaxial compression of a plate, then the number of half waves perpendicular to the load, so in this direction, is 1. It will only have one half wave. So you can impress your friends by telling them that you know you can derive that or prove it, that it will always be 1, no matter what the stacking sequence is, as long as it's symmetric and D16 and D26 is 0. Still, after I set N equals 1 in this expression, I still have M, and if you see the M squared at the denominator, M fourth here, means I'm left with an M squared here. The M squared cancels the second term, M squared in the middle, and it becomes an M squared at the denominator. So actually, there will be some cases where M equals 1 or 2 would give you the lowest, but some cases where M equals 15 or 20 will give you the lowest buckling load. If I plot, because the other parameter besides M is the aspect ratio, so length divided by width is my aspect ratio. I pick a laminate which has the D matrix shown here, and I plot my critical buckling load in newtons per millimeter as a function of aspect ratio, and you will find that that critical buckling load changes with the number of half waves. That is, given this D matrix, if my aspect ratio is less than this value here of around 1.2, 1.4, then I buckle with M equals 1, which means I have only one half wave in that direction. Otherwise, if my aspect ratio is between this 1.4 and 2.6 or so, it buckles at M equals 2 with 2 half waves, and so on. If you increase further the aspect ratio, that is, the length becomes significantly bigger than the width, then you get M equals 3, and you can keep on doing that, of course, ad infinitum. You can get M equals 4 and so on. Interesting is that at the intersections of these curves, the analysis says you have two buckling modes coexisting. That is, the structure should buckle at the same time with one half wave and 2 half waves at this point here at around 1.4. Obviously, in reality, it never happens. There are eccentricities and imperfections which will favor one of the two. And depending on those, you will go either on one of the two, either on M equals 1 or M equals 2. How would that compare now to an equal thickness aluminum? Aluminum is much better. Basically, it can be anywhere between 10 to 20% better. Basically, the exact same equations we derived for composites can be used for aluminum. You just set your E values equal in all directions, and you rederive your ABD matrix, which is much simplified. Then you can actually use the same equation and get the curves for aluminum, which have the exact same shape, one half wave up to 1.4 or so, and 2 half waves up to 2.4. Keep in mind, for aluminum, these are exactly the curve. For composite, you will get this curve for this layup. If you change the layup, it will change the curve. But for purposes of comparison, basically, aluminum appears to be much lighter, or not much lighter, have significantly higher buckling load. But you have to account for the densities, obviously. So if I have the same thickness, aluminum is 10 to 20%, depending on the aspect ratio, better in terms of buckling load. If I now said I want to make my composite to match this, and let's say I want to match the worst case, the 20%. So I say I need to increase the thickness of my composite by a factor 1.2 to the 1/3. And that is 1.063, or I need to increase it by 6.3%. So we'll stop here, but first you'll have to tell me why. How I came up with this. I say I want the composite, which was 20% lower, had 20% lower buckling load, to have a thickness that is given by this quantity, 1.2 to the 1/3. So you expert engineers, how did I get it? That's right, only in thickness. But why is it this value? How did I come up with that? Okay, that's the 20%, very good. Where's the 1/3 coming from now? You are almost halfway there. Only thickness, and so? It is only thickness, yes. Yeah, but it's not the volume. Homsha? Yes, from now on you are excluded on answering any of the questions for the next week or so. But yeah, he's absolutely right. The D matrix, whether it's for isotropic material, we said it's EH cubed over 12 times 1 minus nu squared, or the Dij for a composite material, go like the Qij times Z cubed K plus 1 minus Zk, or whatever we cubed. Now this cubed means that if I want to, and because my buckling load is proportional to the D matrix, remember at the bottom here it's proportional to the D, so I need to increase my D by that 1.2 factor, but because it goes like thickness, where am I? It goes like thickness cubed, then I bring it over to the other side and it becomes 1/3. So that's the 1/3, and therefore that's my 6.3%. If I now try to compare the weights, that means that I have the density ratio, 0.58, that's about the density of carbon and epoxy to compare to aluminum, times my increase in thickness, 1.063, the width and length of the plate stays exactly the same to compare 1 to 1. And I see that the graphite epoxy or the carbon epoxy is 61% of the aluminum, or 38% lighter. So that is very encouraging. You say, okay, composites are 38% lighter, but this is only part of the story. We did this very roughly, and in reality the material, composite material, comes in distinct ply thickness. You cannot get any ply thickness you want, which means when you find this 6.3% increase in thickness, most likely you have to round up to the next ply because it will not correspond exactly to a certain number of ply thicknesses. So that increases your weight. And then if you were to include issues like the effect of damage on environment, you will be doing the environment as part of your homework, then that gets diluted from 38% weight improvement to something significantly less, which will be much more realistic. Any questions? See you Monday.